In this video, we will look at exercises 9, 10, and 11 from the handout 1.1 vectors. Exercise 9 asks to express the acceleration due to gravity vector on Earth, a subscript g, in polar form, rectangular form, and standard vector form. So for the first one, we are going to use the magnitude of acceleration as the positive constant g, acting straight down, and we will take the direction to be 270 degrees. We can also say that the magnitude is approximately 9.8 meters per second squared on Earth. When we convert polar to rectangular form, we take the magnitude multiplied by the cosine of the angle for the horizontal component, and the magnitude multiplied by the sine of the angle for the vertical component. And we know that the cosine of 270 degrees is 0, so we get 0 meters per second squared horizontally, because the acceleration due to gravity vector doesn't act horizontally, it purely acts vertically. And since it's going down, and we are going to take down as the negative, we get sine of 270 degrees is negative 1 times 9.8, gives us the vertical component. Using these two rectangular components underlined in red, they become the coefficients of the I hat and the j hat for the standard vector notation. So we have 0 I hat minus 9.8 j hat, or simply negative 9.8 j hat. In exercise 10, we are asked to determine the direction of each vector, and a quick sketch can help us to see this. The first vector is going left pi spaces and up pi spaces. Because those distances are the same amount, we see that we are forming an isosceles right triangle with the x-axis, which has a reference angle of 45 degrees, or pi by 4. Therefore, the angle in standard position is going to be 3 pi by 4. In the next vector, we see that the vector is acting purely down. A quick sketch can confirm that. And in this is indeed our acceleration vector that we found earlier. And we see the magnitude is 9.8 and the direction is 270 degrees, or 3 pi by 2 radians. The next vector we see is going to the right and going down, so we are in quadrant 4 for the direction. Apart from that, we know that we are going more vertically down than we are going to the right, so we are going to have a steeper angle from our vector measured with the horizontal. And hopefully this reminds us of our basic triangle with a 30, 60, 90 degree reference angle, which we see has a 60 degree reference angle, an opposite of root 3, a hypotenuse of 2, and an adjacent of 1. Because of this, we can see that we have scaled our actual blue vector so that the base is 4 as opposed to the base of 1, and that the height or the altitude is 4 root 3 as opposed to square root 3. So we can see that there's a scale factor of 4 from the parent triangle to the given vector, and therefore the reference angle and all the angles are the same. Our reference angle then is 60 degrees inside here, and the angle in standard position is 360 minus 60 degrees, which is 300 degrees, or 5 pi by 3. So we get an angle in part C, or a direction of the vector of 5 pi by 3. The last vector we see is moving purely to the left, and as a result we have no vertical component, and with the angle is in the direction of 180 degrees, or pi radians. In exercise 11, we're given two force vectors and we want to determine the net force, or the resultant force. This net or resultant force is the result when we add the two other vectors, and we know that we have to add our vectors in rectangular component form. So before we can add F1 to F2, we must convert the vectors to rectangular form. So I'm going to do that directly by taking the magnitude times the cosine of the angle and the magnitude times the sine of the angle for each vector. And we can also write this in standard vector notation so that we can work in a more algebraic way as opposed to working with these brackets. I'm going to have you pause the video and calculate the cosine of 120, sine of 120, sine and cosine of 240, for example. And then we will see how you got on by comparing your answers with mine. So what I've done here is I've recognized the reference angle for 120 degrees is 60 degrees, but the angle 120 degrees is in quadrant 2, and so I've replaced the horizontal component with -8 cos 60 degrees. Likewise, the vertical component is in quadrant 2, so I replaced it with +8 sine of 60 degrees. I've done something similar for the force 2 vector, recognizing that the 240 degree angle is in quadrant 3, and therefore both the horizontal and the vertical components will be negative. I've written them here using the rectangular bracket notation, but then I've taken these coefficients, or these components, and I've calculated the cosine and sine of 60 degrees, and I've written the red vector for F1 in standard vector notation, and I've written the green vector over here for F2. Then I've combined the like terms. We recognize that -4 hat gets combined with -3 hat for a total of -7 hat, and similarly the coefficients of the j hats get combined to give us +√3 j hat. Here we see then that the vector has a horizontal component that is negative and a vertical component that is positive, and so we are going to have a vector in quadrant 2. We're not finished because we are asked to give the magnitude and the direction of the resultant vector, because those are the words that were directly used. So now we need to take the rectangular form of the resultant, or fnet vector, and we need to come up with the polar components. So if we take a look here, fnet we said is -7 hat plus the square root of 3 j hat, and we want to come up with the magnitude of fnet, which we might just call fnet without any brackets or vector bars, or we might refer to as r, the radius of a circle, the hypotenuse of a triangle, the magnitude of a vector. And we find that using Pythagorean theorem with the delta x squared plus delta y squared all square rooted. And so from here we get 49 plus 3, which is 52, all under the square root. And if you've ever used a deck of cards, you know that 52 cards in a deck is made up of 4 suits multiplied by 13 cards in each. So we can simplify this magnitude as 2 times the square root of 13. We were given some units for these force vectors. The magnitudes are given in newtons, so you have to give the units for the magnitude of the vector. Then we want to come up with the reference angle, and therefore the quadrant 2 angle for our fnet vector. And the reference angle is going to be the angle measured to the nearest x-axis, and so theta reference is going to be the tan inverse, or the arctangent, of the absolute value of the vertical component divided by the horizontal component, the opposite over the adjacent, or the slope of the line, but in absolute value because we want the reference angle to be in quadrant number 1. And so here we get that the tan inverse will be taken of positive √3 divided by 7. This is not a ratio that we have memorized special angles for, and therefore the tan inverse of the square root of 3 over 7 cannot be simplified further without a calculator. So we will have the quadrant 2 angle, which you can use a subscript for or you don't need to, is going to be 180 degrees, or pi, minus the reference angle. And therefore we have the magnitude and the direction of the vector.